All right, so let's start. It's time. If at any point you have any issues, just speak up, okay? Because sometimes I'll not be able to see the chat. There's lots of people on the call. And also, if you want, you can turn on your videos. That is completely fine. It actually helps because then I sort of know whether you guys are following or not. Okay. So today we are going to look at subspaces, right? So we saw, I hope you at least saw the video that I had uploaded for the previous lecture. So we covered essentially this, we completed this section on vectors. The first one, vector spaces, right? So we defined what a vector space was, and then we looked at some properties of the vector space. Okay, so we're going to continue with this now. So now we're going to look at something called a subspace, right? So this is also something that you may have seen before, but formally it's defined as follows. So let V be some vector space over the field F. Then a subspace of V is defined to be a subset W of this vector space V, which itself is a vector space over the field, where the addition and scalar multiplications are inherited from the initial vector space. Somebody's asking about attendance. Yeah, I guess it'll just be on Teams. I'm not even sure exactly how the attendance would be marked, but Teams does automatically record this attendance, and I'll forward it to the dean, the academic office, I mean. Okay, so right, and then the note is as follows. So the note is that by inspection of the definition of a vector space, it is easy to see that a subset W of V is a subspace if the following conditions are satisfied. Okay, which is that for each alpha and beta, so for each vectors, for both alpha and beta vectors in W, it has to be the case that the sum is also in W. Okay, it has to be the case that the zero vector is in W. It has to be the case that for each alpha in W, the vector minus alpha is also in W. Okay, and then for each alpha in W, the scalar C, and for each scalar C, the vector C times alpha also has to be in W. Okay, so these are basically a subset of the conditions we saw, of the conditions of being a vector space. Okay, and why a subset? Because a lot of the properties are already satisfied, right? Because we needed some properties about associativity and commutativity from vector addition. And we also needed these properties for scalar multiplication, right? So I'm recalling these. So these do not need to be checked because inherited from V. Okay. Any questions so far? Okay, so if not, yeah, please feel free to ask. Okay, there's no since it's online, it's a little bit less intuitive. So please feel free to interrupt if something is not clear. All right, and so one can simplify things. So one can simplify things further. And so what we're going to now do is we're going to give another definition, essentially, of a subset of a subspace of V. Okay, so consider a non-empty subset W of V. We show that it is a subspace of V if and only if the following conditions are true. That for each pair of vectors alpha and beta in W and each scalar C in capital F in the field, the vector C times alpha plus beta is again in W. Okay, so instead of checking that those conditions are explicitly satisfied, it suffices to check this condition that you look at the subset and you pick any two vectors in the subset and you scale the first vector by C and add it to the next vector and you ensure that this vector is in W. If you can do this, it is essentially the same as saying that the vector, the subspace, the subset W is a subspace, right? Okay, so let's continue. Now we're going to look at the following. So now let's try to prove this theorem. Yeah, there was some feedback saying that maybe give a second to absorb the statement of the theorem. So maybe I can wait a second to see if you have any questions. Is the statement clear? Yeah, actually, I can make it a bit more interactive. Okay, thank you. That the reaction was helpful. Okay, so let us continue then. All right. So suppose that W. Sorry, I don't know why it's jumping around. So suppose that W is a non-empty subset of V, such that C alpha plus beta belongs to W for all vectors alpha, beta in W and all scalars in F. Okay, so we are basically trying to show this direction. Okay, sorry, just give me a second. There's someone at the door, unfortunately. Okay. All right. Sorry about the interruption. Right. So suppose that so we're trying to show this direction, right? So we're assuming that you do have subset W that satisfies these conditions, and we want to establish that it is a subspace of V. So okay, so suppose this is true. Now, since W is a non-empty set, there is a vector rho in W, right? So there has to be some non-zero. Oh, come on. Just give me a second. Ah, God. Thank you so much. All right. So suppose that, yeah, I know it's very unprofessional. There's nothing I could do. I had told them to not come at this time, but anyway. Right. So since W is a non-empty set, there would exist some vector rho, right, which is in W, and therefore minus 1 times rho plus rho has to be 0, right? So why is that? Actually, maybe I can ask you guys. Let's see. I have everyone's names here. Harshit Shah, are you here? Are you around? Harshit? Can you guys hear me? No.
Yeah, we can.
Okay. Is this Harshit? Who's speaking?
Yes, sir.
Oh, Harshit. Okay, perfect. Yeah, can you guys make sure that you can answer questions? It'll be good. Right. So okay. So is it clear why this is the case? Can you justify why minus 1 times rho plus rho is 0? Like why would this property be true, given that W satisfies this premise? Hello, Harshit. Okay. Anybody? Does anyone want to answer?
Since well, we know W is non-empty, so there's a vector rho.
Right. So far, so good.
And And if you multiply a vector by a scalar, then that's also still part of the subspace.
Mm-hmm.
And then by closure, like we can.
No, now you're just saying things. Now you're just saying things. That's not good. If you don't know, you just say you don't know. Okay, don't come up with bogus nonsense. Don't do that. It's not good. So W, right? So the definition of W here, right? It says W is a set, right, that satisfies this property. That if you have two vectors, alpha and beta, in the set W, then C times alpha plus beta is also in W, right? Is that okay? Who was I speaking to? Can you say your
Oh,
name?
Emmanuel. Emmanuel.
Man. Oh no, okay. I thought I was speaking to Harshit. Okay, okay. You volunteer to answer. Okay.
Yeah.
Okay, okay. Then it's fine. Okay, good. Yeah, no, I thought you're just coming up, making up things. Okay, don't do that. Okay, if you're volunteering, that's fine. Yeah. So here, what we're looking at is W, right? So W is a set that has to satisfy this property, right? This is the assumption, correct? And the assumption is saying that if you have two vectors, alpha and beta, then C times alpha plus beta will also be in W, right?
Yeah.
Okay. So now, what choice of C can you use to show this is true? The statement I'm putting in a box now.
I guess you could choose C's -1 and alpha and beta are both equal to rho.
Exactly. So from this we conclude that there is this vector rho, and -1 rho plus rho is 0, right? Because that's just the because minus rho. This is just from the
Yeah.
properties of the vectors,
Yeah.
right? So this is 0,
Yeah.
and so from this we conclude that 0 is in W. Is that okay?
Yeah. That's yeah.
Okay, perfect. Okay, others, if you something is unclear, okay, don't let me keep rambling on, because otherwise things will not make sense. Stop me whenever things are not clear. Okay, it's for your benefit. All right. So now, if alpha is any vector in W, okay, and C is any scalar, right, then we know this is also true, that this vector C alpha equals C alpha plus the 0 vector is in W. Is that okay? So here we chose beta to be the 0 vector, right, and alpha to be alpha and C to be C, right? So we know that scaling of a vector is also in W, so this is fine. Is that okay? Harshit, was the previous thing clear for you? Are you following along?
Yes, sir.
Okay. Let me know, okay, if something is not clear. All right. And then, yeah, actually, I think this is good. Maybe one of you can say, okay, so Harshit, you can stay with me, okay? Stay unmuted, and I'll chat with you as we go along to make sure things are making sense. Okay. All right. So specifically, I hope that's okay. Okay. If you feel shy, tell me. But it's just good. Okay. So specifically, -1 times alpha equals minus alpha is also in W, right? Is that okay? Because we could choose any C, right? So we know C times alpha is in W. So we could choose C to be -1, and that would mean -1 times alpha, which is just minus alpha, right? That is also in W. And this is, so I'm just trying to establish all the properties we needed, right? These are the properties that we want to establish. That alpha plus beta is in W. The 0 vector is in W. For each alpha, minus alpha is in W. And for each alpha in W, the scalar C alpha is also in W, right? So this is the one that's left, right? The other ones are all, I think, done, right? And the last one is what? The last one is just saying that if alpha and beta is in W, then this is in W. How do we see this? Okay, so what is the value of C that we're putting here? Let me ask someone else now. Oh wow, that's a huge name. Yelliseti Prithvi Veera Surya Chakra Pavan. Are you guys around? I'm not sure. Okay. Does anybody want to volunteer what the value of C should be?
C is 1.
Just 1.
C is 1. Okay, fantastic. All right. So now thus W is a subspace of V. Okay, so we've established all the necessary conditions for W to be a subspace, right? That it has to, you know, have the zero vector, the linear combinations have to belong, the negative vector has to belong, and scalings have to belong to the set, and all of these things are true. So therefore, by just starting with the premise, we are able to establish, so starting from here, we're able to establish that W is indeed a subspace, right? So this direction is fine. The other direction is sort of immediate because W is already a subspace, right? And alpha, beta are in W, and so therefore, in particular, they will satisfy C alpha plus beta is in W. Is that okay? All right. Okay, I'll give you just a minute to absorb the proof, and then we can continue. Okay, so let us proceed. Right. So some authors, it turns out, use C alpha plus beta 1, you know, the property that we mentioned in Theorem 1, as the definition of a subspace. Okay, but as we saw in Theorem 1, it doesn't really make any difference, right? Whether you use the definition, the standard definition, which is in this text, or you use the C alpha plus beta definition. Okay, they're equivalent. So the first definition was that it has to be a subset that is a subset that is also a vector space. Right, so this was the definition of subspace. And the other one was that it has to satisfy this C alpha plus beta property. Okay, so these are equivalent. Okay, the crucial point is that if W is a non-empty subset of V such that C alpha plus beta is in V for all alpha beta C, then W is a vector space. Okay, so this is the alternate definition of a subspace. Right, this is what the theorem was saying. Okay, so this allows us to consider many new examples of vector spaces. So let's look at example 6 now. So example 6 says, let's look at trivial example. Okay, so example 6 starts by looking at some trivial examples. So the first one it says is that, you know, we start with some vector space V. Now V itself is a subspace of capital V. Okay, let's see who we can ask now. Manan Sriram Diopurkar.
Yes, sir.
Hi, yeah. Can you tell us why this is indeed a subspace of V? Why V is a subspace of V?
Um,
So
yeah,
let's take a
because
recall.
all the
Yeah. Go.
all the
Go.
criteria for subspace are satisfied, that alpha plus beta belongs to V, negative of alpha belongs to V, and C
Mhm.
alpha also belongs to V.
Exactly. So we just had to show that V is a subset of V, right? And V is a vector space, right? So you don't actually explicitly have to check all of those things, right? So you're given already that V is a vector space, right? So this condition is already true. And V is a subset of itself. Obviously, any set is a subset of itself, right? So both conditions are satisfied. Is that okay?
Yes, sir.
Okay, perfect. All right. And how about the next one? The zero vector alone is a subspace of V. Manan, do you want to also answer this? It seems straightforward.
Uh, I'm not sure about this.
Okay. Yeah, so here we just use the same definition, right? That V is a subset of capital V. Sorry, not V. Let's change this. Let's call this S. Okay, so S is a subset of capital V. Is that true, Manan? So S is just the zero vector, right? V is a vector space, right? And a vector space in particular has zero vector, right?
Yes, sir.
Okay, so the first step is fine. So step 1 is true. What about step 2? So step 2, yeah, then you have to use the definition of a vector space, right? But there's only one element. So essentially, it's not hard to check that all the properties are true. Okay, so I'll leave it as homework. But this is similar to how you were approaching it earlier by checking all the properties. Okay, good. So now let's move on to the next one. Thank you, Manan. So now let's move on to the next one. So in Fn, the set of n tuples x1 to xn with x1 equals 0 is a subspace. However, the set of n tuples with x1 equals 1 plus x2 is not a subspace. Okay, so let's look at the first one. Any ideas? Yeah, maybe we're going very slow, but maybe it's okay. Maybe let's do one more example a bit slowly, and then we'll speed up. Let's see. Who can we ask? Does somebody want to volunteer?
Sure.
Hi, yes. Can you identify yourself?
Emmanuel.
Sorry?
Emmanuel.
Emmanuel. Okay, go ahead.
Right. So the set of examples with x1 equals 0 is subspace because let's consider I'm going to use a C alpha plus B beta definition. So let's assume there's two vectors. Now, if I'm going to scale the first vector by C, then C times 0 is 0. So it's a remaining 0. And then we add it to beta. The first element is going to stay 0. That's still a vector that's going to be of that same form. So it is going to be a subspace.
Exactly. Very nice. Okay, so the proposal was, thank you, Emmanuel. So the proposal was that what we're going to do is we're going to check. So we are given alpha. So alpha is, say, some vector of this form, right? So let's call it x2 to xn, right? And beta is some vector, say y2 to yn, right? Now, the criteria we're using is that C times alpha plus beta should also be a vector of this form. Right? If that is the case, then we've established that C alpha plus beta also belongs to the same set, right? So let's call this set, say, S. So it belongs to the same set S. And if that is the case, then we know from the theorem 1, from the first theorem we proved, right? From theorem 1, we know that S is also going to be a subspace. And so why is that? Well, one can just do a direct computation and check, right? So if you multiply alpha with C, you would get 0 cx2 ... cxn, right? And you would have components from yn, right? So these are the components, right? Sorry, my handwriting is a bit bad, but I guess you can follow. Right, and this is still in the same form as having the first entry 0 and the others are arbitrary. So this is in the set S. Okay. All right. So thank you for that. And then the point is that this next n tuple, where the first entry is defined to be 1 plus x2, and then the other entries are arbitrary. This, it turns out, is not a vector space. Okay, so it's not a subspace of Fn, not subspace. Okay, so this I'll leave as an exercise for you guys to look at. I'll add it in the assignment practice questions. Okay, the space of polynomial functions over the field F is a subspace of all functions from F to F. Does anyone want to? Yeah, okay, let me ask someone. Mitul Chaudhary, do you have any intuition for why this might be the case?
Sir, I'm currently not following. I'm studying from the book, so.
Oh, okay, no worries. Does anybody else want to try to answer? How about? Yeah, go ahead.
So we're trying to prove. So we're trying to say that the space of polynomial functions over the field F is a subspace of the space of all functions from F into F, right? The first is the set of polynomial functions is a subset of the space set of all functions.
Exactly. So let me write it down. So poly subset of all functions. Okay, very good.
And now we also I don't know how to prove formally, but basically you multiply any polynomial function by some scalar, and you do the, basically, and you compose it with some other polynomial, what you end up is a polynomial itself.
Right. So we can just try to use the same property, right? So here alpha and beta, these are going to be polynomials. So if you take the first polynomial, right, and then you take the second polynomial, now c times the first polynomial plus another polynomial is still a polynomial, right? That's it. That's all you have to do, right?
Yes.
Okay, perfect. Okay, so I think you're sort of getting the idea of where we're headed with this. I think I will leave the other two examples as exercises. Okay, so these are fairly simple. Let me quickly mention them. So the set of symmetric matrices happen to be subspaces. Okay, we proved them using a very similar idea. And then also the space of Hermitian matrices, or the set of Hermitian matrices. Here there is a little bit of a subtlety. So the set of Hermitian matrices with is a vector space if the field is of real numbers. Okay. But if the field is complex, then this is not necessarily, then this is not a field, because then c times alpha you'll see will not belong to the set. Okay, so this is going to also be, I'll just mark these as homework for you guys to look at later. All right. Okay, so let us continue then. So example 7 looks at the solution space of a system of homogeneous linear equations. So here we are looking at m cross n matrices over F, right? And we are looking at, so this is, A is fixed, right? This is given to you. And what you're looking at is the set of column matrices X such that AX equals 0. Okay. And the claim is that this happens to be a subspace of all n cross 1. So basically of all column matrices over F. Okay. So yeah, maybe this one last example we can do together, and then we'll move on. Does anybody want to volunteer maybe? How about Avani Mandlik? Are you following along or? Okay. Anyone else? Does anybody else want to volunteer? Try to guess how you, if you've already answered, obviously don't answer, but if you haven't. Okay, so what we really want to check is that it's a subspace, right? So the criteria for checking a subspace we saw is just this, right? That you check that for alpha and beta. So alpha, beta in the subset, we want to show that this is also in the subset or the subspace, whatever. Any volunteers?
Hello.
Hi, yes. Can you identify yourself, please?
Soham.
Soham. All right. Yeah, please go ahead. How would you approach this?
So X is basically a vector, like kind of like it's a vector only. Yeah. So obviously I can
Exactly.
scale it. I can do any operations on that I would do on a normal vector. So obviously it would become like a vector space, right? If I take the set of the solutions, as it's a subspace of the subset of the n cross 1 of the vectors set, right?
Yeah, but it's not so immediate, right? Because it's not just any vector, it is a vector that satisfies this condition, right? So for example, if you took x and you added it with some, say, x prime, right? So ax is 0, but it does not imply that a of x plus x prime is also 0, right? You see what I'm saying? So here x is not the set, it's not an arbitrary set of all
That we have, right?
column vectors. Yeah, there is a restriction, right? So you're looking at x's such that this condition is satisfied, correct?
Yeah, yes, sir, but it's within the solution. So if I add two solutions,
Exactly.
then it will be in the solution set. Right.
Exactly. So you have to be a little bit more careful. So you have the right idea, but you have to, say it a bit more clearly. So what you're saying basically is that if, say, x and x prime are solutions, right? So let me write it properly. Right, so let me write it. So if x and x prime are solutions, right, then ax equals ax prime equals 0, correct?
Yeah.
And then what we want to show is that we want to show that cx plus x prime is also a solution, correct?
So, but we can scale it and it will be like ac into ax is equal to 0 anyway. So when we add those two, it will become.
Exactly. So we just have to do this, right? So if we have cx plus x prime, we multiply it with a, right? This will just turn out to be c times ax plus ax prime. And individually, these two are 0. So therefore, the sum is also 0, right? So I'm just saying that you have to write it down clearly. That's it. So I think you have the right idea, but just be careful, okay? Otherwise, you may lose points unnecessarily for not explaining your thought. Okay. So indeed, that is the answer. Thank you. Thank you, Som. Right, and they try to be a little bit more formal about it. So this I will leave for you to check. The statement is basically just saying that if you have matrices in general of this form, that you have some matrix A, you're adding some scalar. So this part is a scalar, and these are other matrices, right? That you can multiply. They're compatible. Then the result you can essentially just extract the scalar and do the matrix multiplication because it's linear. And this just follows from the definition of matrix multiplication. Okay, and that's what we did. All right, so that was, I think, essentially it as far as the examples were concerned. Now we're going to look at another useful property of these subspaces. So let V be a vector space over the field F. The intersection of any collection of subspaces of V is also a subspace of V. Okay, so let's just take a moment and try to understand the statement. So it's saying, suppose you have V1, right, which is a vector space that is a subspace as well. So it's a subset of V, and this is, okay, let's just say it's a subspace. Okay, so V1 to, suppose V1, V2, V3, so on. These are all subspaces of V. So the claim is that when you take the intersection, so V1 intersection V2, so on, intersection Vn, this is also a subspace. Is the statement clear? Yeah, it's written here. Yeah. So instead of V, they use W. Yeah, let's use W to be consistent. Okay, so let's try to prove the statement. Okay, I thought there was a question. All right, so let's see how to prove this. So suppose that WA is a collection of subspaces of V, right? And W is just defined as the intersection. Now recall that W is the set of elements such that each element belongs to every WA. Right? So this is just restating what it means to be the set of elements that is in the intersection. So basically every element in W is going to also belong to WA. So far we haven't said anything very deep, right? Okay, and then since each WA is a subspace, each one of them contains a zero vector. Is that okay? So WA must contain zero vector for all A. Okay, and so what this means is that the zero vector is in the intersection of all WAs. Okay. Let's see. Let's ask someone. Ansh Prashant Mantri. Can you explain why this is the case quickly? I just explained it. Why so the question is, why is 0 in W?
Hello, sir.
Hey, yeah. Did I ask you
I'm
before
actually,
already? Oh.
no, but I'm like, no, I'm like lagging a bit behind, so I'm just trying to do things correct.
Oh, okay. No worries. Good luck. Yeah. Does anybody else want to explain why 0 is in W?
So it might be because 0 is already a trivial subset of each and every subspace.
Exactly. So this is exactly what we said here, precisely. Okay, thank you. What was your name?
Naman.
Naman. Okay. Right. Yeah. So stay with me. Let's go through the rest of the argument and make sure it makes sense. Okay. So let alpha and beta be in W. Okay, and let C be some scalar. Right. Then by definition of W, both alpha and beta belong to each WA. Is that okay? Naman?
Yeah.
Yeah, you can stay unmuted for until we finish the proof. So basically I can gauge whether you're following or not. Otherwise, it's very difficult for me to know whether I'm going too fast or not.
Okay, sir. Okay, sir.
Okay. Sorry. Okay. Right. So then by definition, both alpha and beta belong to each WA. Right? Is that okay?
Yeah.
Okay. And because each WA is a subspace, right? It must be the case that linear combinations of vectors are also in the same vector space, right?
Yeah.
Okay. And so therefore what we get is that C alpha plus beta is in, because it's in each WA, right? It must also be in the intersection of each WA, right? Which means in particular that it is in W. Is that true? Okay. And so therefore we conclude that W is a subspace of V. So how do we see this? Why is W a subspace of V given everything?
Yeah. Basically, as it's in each of WA, so we are just taking the intersection of all C alpha plus B, and then we are particularly saying that as W is a subspace of V, then yeah, we just proved it.
Yeah, no. So the point is that we were trying to show that W satisfies. So what did we show? We showed that if alpha beta belong to W, then we showed that C alpha plus beta also belongs to W.
W, yeah.
Right? And we already showed that the 0 vector is in W, right? Okay.
Yeah.
And now what was theorem 1, right? So theorem 1 was saying that W of some, which is okay, and W is obviously a subset of V, right? Because it's made of intersection of subsets. So for any non-empty subset, so we know 0 is in the vector space, and we know that it is a subset of V. This thing is a subspace of V if and only if this condition is satisfied. And what is this condition? It is exactly this, correct? Okay, and for C. Right? So therefore one can apply theorem 1 and conclude that W is a subspace of V. Okay, does that make sense?
Yeah.
Okay, perfect. Thank you so much, Naman.
Sir, what if
yes, tell me.
What if we cannot find any alpha beta, which is common in every subspace?
That is okay. So the first part of the argument was that we have to show that W is non-empty. So step 1 is W is not empty, right? Okay, so it could be that W is just this vector, it's just 0. Okay, so then alpha beta will have to just be, because alpha beta you take from W, right? So alpha and beta then will have to just be the 0 vector. You cannot do anything else. So step 2 is saying that suppose that alpha and beta, so it's a premise, right? So it says suppose alpha beta belong to W, then we want to show that C alpha plus beta also belongs to W. Okay, so if it is the case that W is just like the set of one element, then alpha beta are just the same element. Okay, and if W is, if W has many elements, then you're starting with the assumption that there are a bunch of elements in W, and now you're trying to prove that the linear combination, the specific linear combination is also in W, And the way we do that is because W is itself the intersection of all the subspaces, these alpha and beta must also be in WAs, right? Otherwise, they couldn't be in W. So that is how the argument goes. So if alpha and beta here, they belong to W, then by the definition of W, they also have to be in each of the WAs. And then because WAs are subspaces, then the linear combination would again be in each of the WAs, which in particular means that the linear combination would again be in the intersection of all the WAs, which means it will be in W, right? Which is what we're showing here. Okay, I'll give you 1 minute to process that to make sure that you're following. If anyone else has any other questions, you can ask now. Otherwise, we'll just take like 1 minute of silence and make sure we're following what is happening. Okay, let's continue. All right. So now the story is that yeah, maybe we can follow this model. But does somebody want to volunteer to let me know if you're following along? Among the people who are following along, of course. I will just sort of say things and I just want you to nod along or to tell me if you're following. Otherwise, I can go too fast. Any volunteers? Who have we not asked yet? Lavu Darshan, are you following along? Would you like to volunteer? I'm just writing this down so I don't ask you again. And so this is not available. Let's see. Okay, anyone else? Let's see. Divyansh Goyal. Did my connection break? Oh, can you guys hear me still, or did I mess up?
No, it's fine, but I think some people may be experiencing network issues.
Yeah, I figured. Okay. So Divyansh is also not around. What about Radhika Sahu? Oh no, a lot of people are having some network issue. It seems.
Sir, I'll volunteer for this question.
Sorry, are you volunteering? Okay.
Yes.
What's your name again?
Ashwin.
Ashwin. Okay, I'm sorry, I may have messed up the spelling, but yeah, okay, good. Yeah, so let's continue then. So now from theorem 2, it follows that if S is any collection of vectors in capital V, then there is a smallest subspace capital V which contains S. Okay, so this is a bit of a mouthful. So what this is saying is that suppose S is some collection of vectors. Okay, so it's alpha 1 to say alpha k, right? Then the question they're asking is, what is the smallest subspace? Okay, so this is just a set. Okay, and what we want is some subspace V. So smallest subspace V such that S is in V.
Okay.
Small subset W of V. So, okay, does that sort of make sense?
Yes, because V itself is a subspace of V, so every collection of vectors will have some. Is that how it is?
I mean, what we're saying is that you take some, so V is like, say, some huge vector space, right? Let's say it's a Fibonacci vector space, and you have, say, one vector. So you have these two vectors. Okay, so you have alpha1, alpha2, and now you're asking what is the smallest subspace W of this vector space V. Okay, so V is, for example, 3D space, right? And S is say alpha1, alpha2. So you have two vectors. And now you're asking what is the smallest subspace. There's a lot of echo coming somehow. I don't know why. Okay, let's just continue for a bit. So S is alpha1, alpha2. It's just the collection of these two vectors. And we are asking what is the largest, what is the smallest subspace that contains S? Okay. So alpha1, alpha2 belong to alpha1, alpha2 belong to, yeah, let me make them into vectors. So alpha1, alpha2 belong to V. Okay, so let me ask the opposite question. What is the largest subspace?
V itself.
Exactly, right? Exactly, perfect. So the largest subspace is V itself, and now we're asking what is the smallest. Okay, and from theorem 2, we sort of have some handle on how one might think of the smallest, because so theorem 2 is saying that you take the intersection of all subspaces, right? So this was saying intersection of subspaces is also a subspace, right? That's what we just proved, right? So this allows us to sort of think of a notion of the smallest subspace. So what we can say is that you take all possible subspaces that contain the set S and you take their intersection, right? So if you do this, you will have a unique subspace, right? Because the intersection is well defined. It's a unique object. Is that okay?
Yes.
And then finally, because it's a unique thing and nothing can be smaller than this, right? It must be the smallest, because if it was smaller, then the intersection with this new subspace would have made the unique subspace smaller. So suppose that say W is the smallest subspace. Oh, yeah, so no, let me say the following. So W is, is the intersection over all Wi's, where these are the subspaces containing S, right? So suppose this is how we define W, then I'm claiming that W is the smallest subspace, right? Because suppose it was not, right? So suppose W prime is smaller and yet S is contained in W prime, right? Then we have a contradiction. Okay, so what is the contradiction? The contradiction is that W is the intersection, right? Already is the intersection. So obviously, if it was intersecting with W prime, it cannot be bigger than W prime. So it has to be this. Okay, so therefore, this is the intuition for why one can ascribe the notion of a smallest subspace associated with a set of vectors S. Okay. Is this okay? Yeah. Okay, fantastic. All right. So now we come to the formal definition. So the formal definition says the following. So let S be a set of vectors in a vector space V. The subspace spanned by capital S is defined to be the intersection W of all subspaces of V which contain S. Okay. So yeah, maybe I should highlight this subspace spanned by S. This is the definition of what it means to be a subspace that is spanned by S. Okay, and then it goes on to say that when S is a finite set of vectors, this is just notation. Okay, this is notation. Then the subspace spanned by the vectors. So W, the thing that we defined above, is called the subspace spanned by the vectors alpha1 to alpha n. Okay, I'll give you 1 minute to digest the definition and let me know if you have any questions. Well, about 30 seconds, not 1 minute. Okay. To the people who were asking questions earlier, is it clear? Is it obvious? Is it trivial? Was it Manan? Was it Manan, Emmanuel? Do you guys? Does it make sense? Is it straightforward?
Yes, sir.
Yeah.
Yeah.
Okay. Okay. Perfect. Okay. So let's continue. Right. So now the definition is not very constructive. Okay. So what I said is like, oh, you look at the set of all subspaces and you take the intersection, or you take the smallest subspace that contains the set, yada yada. It feels a bit complicated, but turns out that there's a much cleaner definition. A much cleaner constructive way of defining the same object, and theorem 3 basically shows this equivalence. So what it says is that consider the subspace spanned by the non-empty set S of this the set of vectors in this vector space V. Okay. This is basically just using the definition above. Okay. It turns out that this subspace that we defined above is exactly the same as the set of all linear combinations of vectors in S. Okay. So suppose that S was, say, alpha 1 to alpha k. So subspace spanned by S, right? So this object that we defined above, this, it turns out one can characterize as follows. So this is just the set of vectors C1 alpha 1, Cn plus alpha alpha k, sorry. Okay. Where you're taking C1, C2 to be. These are just scalars in the field. Okay, is the theorem statement clear? Yeah, I need to. Does somebody want to volunteer for this part of the discussion to help me guide me with whether you're following or not?
I'll volunteer. So,
Okay, perfect. So is the theorem statement okay?
yeah, it's great.
Okay, perfect. So let's continue then. Right. So now let L be the set of all linear combinations of vectors in capital S. Okay. So this is basically just taking this set, right? So this is basically L. And let W be the subspace spanned by capital S, right? So W is the vector space. This thing is W, right? That we wanted to talk about, and we want to prove basically that W is L. So the goal is W is L, right? That's what we want to do. And the way we will do it is we'll first show that L is a subset of W, and then we'll show W is a subset of L. Okay? That is the strategy. Perfect. All right. So then let alpha 1 be. But what have I written? Okay, I think I was sort of in the middle of writing something. So let alpha 1 to alpha m be let this be S, right? That's the set of vectors that we're interested in. Then each linear combination alpha, right, which is just some linear combination of vectors alpha is in S, is clearly in W. Okay, is this statement clear?
Yes.
Right. And why is that? I mean,
Because,
it's trivial, I know, but is this
because
just
W
yeah.
is because W is a subspace.
Exactly.
By the properties of a subspace, multiplication with a scalar and addition to another vector in that subspace would result in the resulting vector would also be in that subspace.
Right, exactly, perfect. Right, so this is it's clear that linear combinations will be in W because W is a subspace that contains these vectors. Like what was your name again?
Tanisha.
Tanisha, Tanisha. So yeah, okay, so that's exactly like Tanisha said. So now we conclude that L is in W, right? Because we've shown that every linear combination is already in W, so therefore this part is done. This is straightforward, yeah?
Yes.
Okay, now what we're going to do is we are going to see how W is contained in L. And we observe that it is enough to show that L is a subspace containing capital S. Okay.
Okay.
And why is that? Because W is the smallest subspace, right, that contains S. So any other subspace that contains little s must necessarily contain capital W, right?
Yeah.
Okay, perfect. All right. And then we note that capital L contains capital S and is non-empty. So capital L obviously contains little s, right? Because we can take the linear combinations to be, just we can take C1 to be 1 and then C2 onwards to be 0 and so on, right? Or more precisely, one can take Ci to be 1 and Ci or k to be 0 for all k not equal to I, and then you can make this choice for each I. One can make this choice, right? So clearly this is the case that you can choose the vectors. And now if alpha and beta are in capital L, so this is fine. It contains S and it's non-empty. And now the claim is that L is a subspace, right? This is what we want to establish. And how do we establish a subspace? Well, we play the usual game, right? So we showed earlier in theorem 2, I suppose, that to establish a subspace, we want to show that if alpha and beta belong to L, then we want to show that C alpha plus beta also belongs to L, right? That's the approach we want to take. So let's start. So suppose alpha and beta belong to capital L, right? Then alpha is a linear combination of these guys, right? And this has to be the case just because of so this is just from the definition of capital L, correct? Because capital L was just a set of all linear combinations of alphas.
Yeah.
Okay, brilliant. And then similarly for beta, one can write this.
Okay. Yeah.
Wait, so but what is beta? I thought it was just alpha. I'm getting confused now. So we're writing beta as linear combinations of.
I think we can just write it as y1 alpha 1 and so
Yeah,
on.
it should
Since
be
alpha
alphas,
represented the vectors.
Yeah, I don't know why I wrote it as beta. I hope I'm not missing something. Doesn't change the argument, but okay, this is something I need to do for me to check, double check. But it looks like one should be able to take alphas here, alpha 1 to alpha m. But it also has n. I think I just messed up here. Okay, and okay, so alpha and beta belong. Oh no, but they don't necessarily have to have. It is correct. Oh yeah. Okay, so it should be m. Then it's fine. Okay, ym, y1. Right, and now for each scalar that we take, right, then we just get a linear combination. Well, it would be cxi plus yj times alpha I, right? If I'm substituting with alphas, right? And then this clearly is also a linear combination, so this will be in capital L. And so what that establishes is that if alpha and beta are in L, then C alpha plus C beta is also in L. So it also belongs to L. And so therefore we conclude using the theorem that L is a subspace. And we already established that the only thing we need to do is to show that L is a subspace that contains S. So that establishes the proof. Is that okay?
Yeah.
Okay, thank you so much. So that was good. I will give you like just a minute for everyone else to make sure that the statement is clear. Oh, sorry, the proof is clear. And then we can continue. I'll shut the door in the meantime. Also, maybe one of you can decide to if they want to volunteer when I come back. You can make up your mind in the meantime. All right. Does somebody want to volunteer? Or oh, I know what to do. Tanisha, right? Do you want to nominate someone to volunteer? I think maybe that might be better because you might know who else is following along better than I would.
I'm actually not sure, sir, since I'm in my room. I don't use connections.
Oh no, I mean in general, right? You must know who, because I think there are some people who are just studying by themselves, right? That's what I was asking.
Yeah.
You don't know, okay. Okay, let me just make a random request and see if they're willing. Palem, what is this? Palem Shamatmika. Are you around? Okay. How about Gnaneswar? I think a lot of people are having. Okay. Hi. Would you like to volunteer to follow along? Okay. Thank you so much. I'm sorry. I know I'm putting you on the spot, but it really helps because otherwise on Zoom it's very hard to tell, right, whether anything is making sense or not. So thank you. All right. So now the story is as follows. So in view of this, one can equivalently define a subspace spanned by alpha 1 to alpha n as just the set of all linear combinations of these vectors, right? Which is just this object, right? So you just take linear combination. This is what we essentially showed, that it doesn't matter whether you take the definition in terms of the smallest subspace or in terms of linear combinations of the vectors defining the set. Is that okay?
Yes, sir.
Okay, perfect. All right, so we now introduce some notation to easily speak of linear combinations of vectors that are contained in different sets. So the first definition is as follows. So if S1 to Sk are subsets of a vector space V, the set of all sums alpha 1 to alpha k of vectors alpha I in capital Si is called the sum of the subsets S1 to Sk, and it is denoted as such. Okay, so it's a bit of a mouthful, but all that it's saying is that if I write, so suppose S1, S2, and so on, Sk, they have so they each contain they are subsets of this vector space, right? So the subsets of this vector space V. Okay, then the set of all sums. Okay, so we're going to, so suppose for simplicity, okay, let's suppose these just have one element. So suppose this has, say, yeah, let me do it with 3. Okay, it'll probably be easier. So S1, S2, S3. Okay, so suppose this is alpha, this is beta, this is gamma. Okay, so this has, okay, so these are vectors. So this is how you define the set. Is the notation clear? Wait, what was your name? Who volunteered?
My name is Gnaneshwar.
Naneshwar. Like that? Okay. Yeah, so is it clear, Gnaneshwar, what I'm saying? So I'm just saying that you take 3 sets, subsets of V, and suppose that the vectors they contain are alpha i's, beta i's, and gamma i's. Is that okay?
Yes, sir.
Okay. And then S1 plus S2 plus S3 is basically just the following. So it's alpha I plus beta j plus gamma k. Okay, so it is just this set with I, j, k. Okay, so you take one vector from the first set, take one vector from the second set, take one vector from the third set, and just add them up. Okay, and you take them in on all possible combinations, and whatever set you get is called the sum of the subsets. Is that okay?
Yes, sir.
Okay, okay. Tell me, okay, if something is not clear. Okay, so this notation becomes handy when one considers, why is it missing some text? Strange. So when one considers subspaces. Okay, so the subspace, so what we're going to do is now, so suppose that W1 to Wk are subspaces of V. Okay, then this sum W, defined as the sum of W1 to Wk, can easily be seen, can easily be seen to be a subspace of V, which contains each of the subspaces Wi. Okay, do you want to, what was your name? Gnaneshwar, do you see this? Do you want to attempt to prove? Gnaneshwar, are you there?
Sir, I'm there.
Yeah, you can keep yourself unmuted. You don't have to mute every time. It's okay. It's okay. That's the whole point. That I can sort of get some feedback. So, okay. Does anyone want to try to prove it? The usual suspects: Emmanuel, Manan, maybe Tanisha.
Yeah, sure.
Okay. Okay. So, how do you see this? So I'm trying to see how to prove this, right? That if W1 to Wk are subspaces, then we want to show that the sum W is well, it contains each of the subspaces Wi.
Yeah. All right, then we have. All right, so all of them are subspaces. So, I might be.
Right, so let's try to do it for W1, right? So if you want to show that
Yeah.
W equals W1 plus ... Wk. So if you want to show, so the goal is to show that W1 is contained in W, right?
Right.
So
Right.
so one way of doing it could be that, we know that. Yeah, go ahead.
All right. All like just take all the other alpha k
Exactly.
except for 1 to be 0.
Exactly, right? So because Wi's are vector spaces. Oh, sorry. Yeah. Okay, we can just read the vector spaces, right? They contain the zero vector, right?
Yeah.
And then we can do exactly what you're saying, right? And so then W1 plus 0 plus 0. So one can do that, right?
All right. Yeah.
So this would be equal to alpha 1, and so therefore W1 is contained in W. Okay. So
Yeah.
right. Yeah, so sorry, it was straightforward, but just to make sure that the notation is clear and so on. All right. Any questions about this? Okay, so if not, let's continue. And then there's this small little claim here that says if W is the thank you. It was Emmanuel, right?
Emmanuel.
Yeah, thank you. Right. So let's continue then. So the claim is that W is the subspace spanned by the union of W1 to Wk.
Right.
Okay. So how do we see this?
It's
right. So the note above. Yeah.
Yeah, we know that all the W1 to Wk are subsets of W. So we can assume that their union is also a subset of W.
Right. And theorem 3 was saying what? That you can take linear combinations.
Yeah.
the span of yeah, basically, yeah, you're basically spanning all the vectors, right? That's what the point is. Okay. So that's the thing. But I'll leave it as homework to write it down properly. All right.
Oh.
Okay, yeah, thank you. So let's continue then. We have right. Okay, so at least let's try to finish 2.2, maybe 2.3. I'm just trying to see if we can maybe get to a theorem. Okay, I think it would probably be ambitious to get to theorem 4, but let's see. I'll maybe leave a recording, okay, if we don't manage to make progress, but let's continue. So example 8 is saying the following. So let F be a subfield of the field C of complex numbers. Okay. So one can take alpha 1 to be this vector, alpha 2 and alpha 3 to be these vectors. Now W is so it's saying let W be the subspace spanned by alpha 1, alpha 2, alpha 3. Okay. And then by theorem 3, we know that a vector alpha is going to be in W if one can express alpha as a linear combination of these individual alphas. Okay, so we're just trying to solidify what we learned. So let me start again. So consider these vectors, okay, and we are going to think about the subspace spanned by alpha 1, alpha 2, alpha 3, right? This is what we want to look at. There was to sort of build some intuition about it. So let's call this subspace W, right? And from theorem 3, we know that alpha is going to belong to W, right? This is equivalent to saying that there exists some scalar C such that alpha is Ci alpha I, right? Oh shoot, I forgot to ask for a volunteer. Does somebody want to volunteer for the last 15 minutes maybe? Maybe I should ask someone. Kwazukuli Ram Kumar. Are you able to hear us? Are you following? Do you want to volunteer? It's a bit hard to find volunteers. I thought it would be a little bit easier. Right, let's see. Feel free to volunteer yourself. Okay, I'm just trying to encourage you. Oh, do we have a volunteer?
Jayant.
Hi, can you identify yourself?
My name is Jayant.
Jayant. Okay. Thank you, Jayant, for volunteering. Let's continue. Right. So far it makes sense, right? So by theorem 3, we know that alpha can that there exists scalars such that alpha can be written like this if alpha belongs to W, right? Is that okay?
Yes, sir.
Alrighty. So now, so W consists of all vectors of this form. So alpha is C1 plus, not plus. So basically, you just take the combinations with C1s, right? You substitute the vectors. So we can quickly do that. So here we have C1 because this was 1. The coefficient, the second coefficient of C1 is 2, right? Because this is 2. And then in the third one, there's no contribution, right? In the fourth one, there's 3, right? And then the fourth one, there's no contribution, right? So basically, we're just writing out this expanding alphas, right? Is that clear?
Yes.
Perfect. All right. And alternatively, one can describe, alternatively, W can be described as the set of vectors alpha, which are just x1 to x5, which satisfy these constraints. Okay. So I'll give you just maybe 10 seconds to see if it makes sense to you. Otherwise, I'll explain it. So you just have to stare at what we wrote for alpha and see if, instead, if you wrote alpha as x1 to x5, what constraints would you put? What constraints would you add? X's would give you.
So here we're taking C1 as x1 and then
Exactly.
finding it same way as above.
Exactly. So precisely. So you basically just equate it with C1 to C1, C2, 3C1 plus 4C2, comma C3, right? You make the comparison and then you eliminate C's and you'll get these equations. Is that okay?
Yes.
Perfect. And then what is nice is now you can check. So this I will not do explicitly, but one can check that this, for instance, is not in the subspace. Is in the subspace, while the latter is not. Okay. So okay, is the example sort of making sense? We're just trying to get some intuition about what it means to be a subspace spanned by a bunch of vectors.
Yes, sir.
All right, thank you. So let's look at another example then. Yeah, so maybe example 9. Let's see. Okay, so the example 9 says let F be a subfield of the field of complex numbers. Okay, and let V be a vector space over all 2 × 2 matrices in F. Okay, is that fine? So V is just A, B, C, D, where A, B, C, D belong to F, right?
Yeah.
Okay. And now what are we saying? We're saying that let W1 be the subset V consisting of all matrices of this form. Okay, where X, Y, Z are scalars in F. So, okay. So can you see that W1 is at least a subset of V? Right.
Yeah.
Okay. And exactly. All right. And now we want to prove that W1 is a subspace. Right. So how would we do that?
Since W1 is a subset of V and
yeah, we have to do that the usual thing, right? With C alpha plus beta. Exactly. So here, you can sort of look at the matrix. It'll be X, Y, Z, 0. You can multiply it with C, and then you'll have X prime, Y prime, Z prime, 0, right? And the form is preserved, right? The last entry stays 0. So you know that this is a subspace, right? Okay, good. Is that okay? Does it make sense?
Yes, sir, makes sense.
Okay, perfect. And then one can do something similar with W2. It's just diagonal, right? So one can check that W1 and W2 are both subspaces of V. This we just did. And also V is, so if you define V as, if you consider, say, V prime as W1 plus W2, okay? So what is this going to be? This is going to be the set of all vectors Z, right? And plus you're going to have X prime, Y prime, right? So it is the set of all such vectors with X, Y, Z, X prime, Y prime, all belonging to F, correct?
Yes, sir.
Okay, and now we just want to argue that V prime is actually equal to V, right? Which is straightforward, right? Because so this matrix that we're writing is just X plus X prime, Y, Z, and Y prime, right? So this is basically so one can show both ways, right? So one can show V prime is a subset of V. Because these are just elements in F, it's obviously an element of this is already in V, and to show V is in V prime, any V that you're given, you can just set X prime equal to 0, right, and you'll get it.
Yes,
Right? Okay, good. So that was the second part. And finally, the last claim is that the intersection W1 intersection W2 consists of all matrices of this form, but you just have this entry.
yes.
Right, because those are the only common elements, right? Or none of the other matrices are common in these. Okay. Is that okay? Is that clear?
Yes, sir. Makes sense.
Okay, perfect. Right. Yeah, so maybe section 2.3, I will maybe record and send you a recording. Let's just go through the other 2 examples here. Okay. So now example 10 says the following. So let A be an M cross N matrix over a field F, okay? And row vectors of A are the vectors in Fn given by AI. Okay, so this is not saying anything, right? It's just saying like if you write a matrix, then this thing alpha I is the row vector associated with the matrix. Is that clear?
Yes.
Okay, and then the subspace Fn, subspace of Fn spanned by the row vectors of A is called the row space of A. Okay, so these are mostly just definitions. This is just notation. Okay, so the subspace spanned by the rows is called the row space of A. Okay, and now it says that in the subspace that we considered in example 8, right? So in example 8, we looked at, do I have a screenshot? No. So in example 8, remember we looked at these alpha 1, alpha 2, alpha 3, right? So
Yes.
if you make them into a matrix, you'll get this, right? 1, 2, 0, 3, 0, 0, 0, 1, 4, 0, 0, 0, 0, 0, 1, right? So there's the matrix A that they're calling, and then they're saying that the row space of A is what we were considering in example 8, right? Is that making sense? Or? Okay. Sorry, the connection's a little bit poor sometimes. So, right, so this is exactly the matrix A that we were talking about. And here's like a small little exercise you can check that the row space of the following matrix, which has an additional row, right? Even though it has an additional row, the row space is the same. Row space of B equals row space of A. Is that okay?
Yeah, since it still follows the form of C1 to C1. And so
Exactly. This is just a linear combination. Fantastic. Okay. So that was that. And then the last example is the following. So we consider the space of all polynomial functions over F. Okay, so V is the space of all polynomial functions now. And suppose that S is a subset of V consisting of monomials essentially. Okay, so monomials are defined as follows. So F0 is just a constant, is like 1, F1 is X, and so on, right? Fn is X to the n. And then the claim is that V is the subspace spanned by the set S. So span of S equals V. Okay. And how does one do this? One can just use the definition of adding coefficients, right? So you can just say that Ci Fi sum over I. Right? This would be the span of S, right? For arbitrary
values of CM.
Exactly. So for arbitrary CIs, Ci in F arbitrary. Okay. So these would give you all the different functions, and basically this spans all polynomials, right? Because a polynomial is basically just some coefficient. Well, actually, one can be even more explicit, right? This would just be x to the n, oh sorry, x to the I, right?
Yes.
Where I goes from 0 to whatever. All right. So that sort of does this part. Okay, so we still have 2 more minutes, so at least I can give you some intuition about what we're going to do next. All right, so far what we've looked at is we looked at subspaces, right? Now what we're going to do is we're going to generalize the notion of dimensions. Okay, so normally we think of dimensions as, one-dimensional objects or two-dimensional objects, right? It's more a geometric thing, so which is usually geometric. But now we're going to extend it to vector spaces, and we want sort of an algebraic definition for doing this. And in order to do this, we go through the concept of something called a basis for a vector space. Okay, so let me quickly at least tell you the definition of a basis. Okay, so before I define a basis, I'll need to define something called linear independence. Or linear dependence. This is stuff you've already seen. So let me quickly at least state the definition. The definition says the following. So let V be some vector space over F. A subset S of V is said to be linearly dependent or sometimes simply dependent. Yeah. If there exist distinct vectors alpha 1 to alpha n in S, and scalars that are not all 0, such that the this sum over here is 0. Okay, so linear dependent is saying that you can just take linear combinations and make them 0 without all c's being 0. So then we would say that the set itself is linearly dependent, and we say a set is linearly independent when the previous property is not true, that you cannot find any linear combination that would make it disappear, except unless all c's are 0. Okay, and if the set contains only finitely many vectors, alpha 1 to alpha n, we sometimes say that alpha 1 to alpha n are independent or dependent instead of talking about the set. Okay, so that'd be all. I think we've hit the time. Thank you so much for your patience. I'm sorry. I hope to get well and be able to do the lectures in person again, but hopefully it wasn't too bad. Okay, take care, you guys. Goodbye. Thank you.